brief video about an extended version of the fundamental theorem. Remember, there's one version of the fundamental theorem that talks about differentiating an integral as long as the integral has a variable upper endpoint. And that's the version we did second. It's the version they do first in the book. But I want to look at something that's a little different. What happens if I have a function, like an integral here, that's got an integrand, and then I integrate from some constant to a complicated variable upper endpoint, not just x, and then I differentiate that with respect to x. So we want to compare to the standard version of this half of FTC, which says that if I take the derivative of an integral with a fixed lower endpoint but a variable upper endpoint, then I just get the value of the function of the upper endpoint. I just get back to exactly f, and I do not have to do any work. That's great. Okay. Well, but it would be a little bit too much to ask if that would be true if this guy were also, if this were not just x. And there's a pretty easy way to derive the more complicated version, though. It turns out to just involve adding the chain rule. What we're going to do is we're just going to introduce a little notation. We're just going to say, suppose this did have an x. In our example, we're going to define big F of x to be equal to the integral from 0 to x of t cosine t plus 1. Well, that's a plus, not equals, dt. That's not exactly what we're analyzing here, but it's close. And what we want is the derivative of big F with not x plugged into it, but x cubed plugged into it. So that makes it clear what's new about this. It really is very, very similar to the standard FTC here. It's just got something new plugged in. And the thing is, when you plug something new in, calculus says you have to be real careful about that, because the derivative of this with x cubed plugged in is not just f prime. That's not just f prime of x cubed. We know better than that. We know that the chain rule tells us something else. We know that that's equal to f prime evaluated at x cubed times the derivative of x cubed times 3x squared. Well, how does that help us? Okay. Well, this function f is defined in a very funky way. It's defined as an integral. And you could actually go ahead and calculate the formula for this with some effort, but in fact it's not one we know how to do. And it's not important to be able to do that here, because as soon as we integrate it, we're going to be differentiating it. So, because this is a function defined as an integral, even though that's a weird thing to do, the one thing that's easy to do to such a function is to differentiate it. And notice what's going on here. On this side, I plug in the x cubed to get this thing, and then I differentiate. That's what I really want to evaluate. But the chain rule says, if you're careful, you can basically do it in the opposite order. You can instead first take the derivative of the function without worrying about what you plug in first. So take the derivative and then plug in x cubed. And the reason you can do that is you actually do have to correct it with the chain rule. We know how to correct that. It's not true that you can just switch the order of plug in and differentiate. You can differentiate and then plug in the x cubed if you correct with the chain rule. And so the reason this is good is that this f prime is the derivative of this guy ignoring any kind of change you made to the upper endpoint. And so f prime is exactly just this function. Okay, so the FTC says f prime of x is just equal to x cosine of x plus 1. And so now I just plug in the x cubed. So everywhere I see an x instead, I put in an x cubed. And then I do have to multiply by the chain rule to make it correct. And so what does that amount to? It amounts to, the answer to this was, yes, you plug in the upper endpoint everywhere you see a t in here. That gave us this. But then you also have to multiply by the derivative of what you see up here, because that's what the chain rule is saying. Whenever we plug in something new instead of x, and we differentiate, we always have the chain rule. Okay. So the formal version of it, which you'll see in the book, is that the derivative, we just need a few letters and names for things. Let's say this is g of x of f of t dt. Remember, the t here has to be different from x, because that's a temporary variable that runs along the interval of integration, whereas x is controlling how far you go, where the right endpoint is. So what it says is, you take f and you plug in what you see in that upper endpoint. That's analogous to what we would do here, but then you have to multiply by g prime. So you can see it looks exactly like the chain rule, except there's no prime on f. The reason for that is you took f, you integrated it, and then you differentiated it so it goes back down to just ordinary f, plug in g, and then multiply by the standard chain rule factor. And the example of that is right here. Okay, and so that'll help you do the one problem that I assigned on this subject.